Hello students. Today we're going to be taking a look at section 1.3, graphs of functions. Objectives, students will know how to analyze graphs of functions. So first thing we're going to take a look at is the graph of a function. It says because y equals f of x, graphing functions is no different from graphing equations in two variables. Observe the graph of y squared equals x and see if this graph is the graph of a function. We already discussed this back in section 1.2, where if you would want to get this in terms of y as a function of x, remember the question begs, is y a function of x? Well, let's see. If you try to get y by itself, you need to take the square root of both sides. If you take the square root of both sides of this equation, so what? Y equals square root of x, but what? Plus or minus also needs to be assigned here. You're actually looking at y as a function of positive root x, but y as a function also of negative root x. In other words, y sub 1 and y sub 2 have to be designated as two separate functions in order to graph this. Turns out, of course, that in its entirety, plus or minus root x is not a function. It's a relation. And the graph, as we already know as well, does nicely speak to this. So if you were to type in y sub 1 as positive root x and y sub 2 as negative root x, it would, if you recall, fail the vertical line test. And speaking of that, this leads to the vertical line test, which states if every vertical line meets the graph of a relation at most one point, then the relation is a function. And as I just said, this particular graph, but also this particular equation, is technically not a function, as we proved. Example 1. Which of the following graphs are graphs of functions? So you can see here this parabola that opens down. If you were to draw a vertical line, it does in fact only go through one point. Because it passes the vertical line test, yes, it is a function. Part B, you've got this ellipse graph. Drawing a vertical line, you're going to see that it goes through 2 points maximally. And that's the other thing. If you draw a vertical line such that it goes through the most number of points possible, it's going to end up being 2 points maximally. So no, it fails the vertical line test. It is only a relation. It's not a function. All right, moving on. Example 2. It says find the domain of the function f of x equals the square root of x plus 1. Now with a square root function, or any even root function for that matter, the radicand, as you know, cannot be negative. If it's negative, then we technically can't graph it because that would lead to an imaginary solution. We're going to be looking at obviously only graphing real numbers and real number solutions here. So we're going to identify that the radicand, in other words x plus 1 here, must be greater than or equal to 0. So we know it has to be positive. If we subtract 1, and you solve, you can see here x must be greater than or equal to negative 1. Therefore, the domain is from negative 1 to infinity. The graph of this function, and it is a function because it passes the vertical line test, the graph of this function starts at negative 1 and proceeds to the right, as you can see. So negative 1 to infinity. Increasing and decreasing functions. We're going to draw the graph of any polynomial. In this case, more specifically, f of x equals x cubed plus 3x squared, which I have here for you. I've already done that on the calculator. Labeling the extrema at negative 2, so negative 2 comma 4, and 0, so 0, 0. Now, extrema, if you recall from Algebra 2, speaks to a maximum or a minimum of a function. Sometimes you'll even hear us discuss or describe this as a relative maximum or a relative minimum. Specifically, that's what these 2 points are. So the extrema here, this negative 2 and 0 x coordinate value are what we're identifying here. It also says identify any intervals over which the function is increasing. Do the same for decreasing. Use intuition to develop the following definition. So as it turns out, the function is going up or increasing from left to right between, well, we could say negative infinity to the left all the way up to negative 2. It's decreasing between negative 2 and 0, and then it's increasing again from left to right from 0 off to infinity. We're going to go ahead and use notation for increasing, decreasing, and then also constant intervals. but that's just kind of a nice generic way to depict this graphically. A function f is increasing on any interval if, for any x sub 1 and x sub 2 in the interval such that x sub 1 is less than x sub 2, then f of x sub 1 is less than f of x sub 2. So it's essentially saying that a point here at the bottom of the graph has a smaller y value than a point, let's say here, up above it. Now notice the x is less than here, the x, let's say here. So the graph appears from left to right to go up and to the right, just like it does here. So those two are increasing by virtue of, again, how the x's and the y's play out. It's decreasing. I won't bore you with the notation, although it is, again, important to at least understand that any x value here is less than any x value here, but at the same token the y is larger here than it is there. So the graph goes down and to the right. That's a really easy way to remember that, frankly. Decreasing down and to the right, increasing up and to the right. A function f is constant on an interval if for any x sub 1 and x sub 2 in the interval, then f of x sub 1 is equal to f of x sub 2. Now we don't see that in this particular graph, but a constant interval will be quite literally a horizontal segment or part of the function that doesn't go up nor down from left to right. So constant intervals we'll definitely have to know about as well. Moving on here, example 3. This is going to ask you to determine the open intervals on which this cubic function is increasing or decreasing. So we get more specific in identifying the actual notation and interval notation more specifically of increasing, decreasing. I identified my relative max here at -2 for the x and here at +2 for the x. I didn't actually note the y value. I don't need the y value at all when I write my answer for increasing. So increasing and decreasing for that matter. So increasing, as you can see, up and to the right from -infinity. So off from -infinity up till you get to -2. And then it's increasing again from 2 off to infinity. It's decreasing again down and to the right between this x value and that x value. So this x value was -2 and this x value was +2. So there you go, decreasing between -2 and 2. And notice we use parentheses at all extrema x coordinate values. That helps us kind of designate and depict how the interval is changing. And it's consistent as you go through. Relative minimum and maximum values. So note the following definition. F of a is a relative minimum of the function f if there exists an open interval I containing a such that f of a is less than f of x for all x in I. Relative minimum and also relative maximum are things that we've seen. I actually described that in the last picture up above. On this particular function graph, you can already see, well, here's the equation. F of x equals -3x squared minus 2x plus 1. I've already graphed it for you. And because the question asks you to use your calculator to estimate the relative max, if you recall, you can hit second, trace, option number 4, which is the max button. You'll hit enter on a left bound to the left of this approximate x coordinate. You'll then scroll to the right, hit enter on the right bound, and then you'll hit enter on guess. When you hit enter on guess, it will give you the guess, roughly speaking, as you see, -0.33, 1.33. The relative max, and again, this definition really speaks to both min and max, speaks to, again, how the graph increases, hits a point of which it doesn't technically go up at all anymore, and then it goes down. So increasing and then decreasing. Very easy concept to understand. Let's move on. Example 5. The profit for a new company can be modeled by the following. So we've got P equals 0.225x cubed minus 17.21x squared plus 315x plus 132.1, where P is the profit in thousands of dollars and X is the number of units sold in thousands. what would be the maximum profit for this company? So yet again, I typed this on the graphing calculator. This is just a different kind of graph that I was able to pull from more quickly. Another option for us. Turns out if you use the relative max feature, second trace, option 4 again, left bound somewhere here, right bound somewhere there, you'll get a max of 11.94. And again, the number of units is sold in thousands. And the P, or profit, the Y coordinate, ends up being in thousands as well. So this quantity on your calculator ends up being the Y value, but technically because it's in thousands, you have to move the decimal point 1, 2, 3 places to the right, because again, if it's in thousands, you got to move it in that direction, 3 places. So there it is. There's your profit. Let the calculator do what it's able to do for you. Getting that relative max without a calculator would be virtually impossible. So please take advantage. Graphing step functions and piecewise defined functions. There is something called the greatest integer function. This is the notation for it. It essentially means that it's the greatest integer less than or equal to x. This is an application that it's commonly used in. We are going to dedicate a little bit more time later to this concept, possibly later. The rest of this little section, though, the more important piece really is the piecewise defined function. It says, note how to graph piecewise defined functions by drawing the whole graph for one part of the function on the board or on my notes here, and then erasing the part that you don't want. Now, it says on the board, I guess we can say on OneNote or on your piece of paper. Sketch the graph of, here it is, the piecewise defined function. You've got a piece 1 that looks like a linear function wherein x is less than or equal to 2. Piece number 2, again a linear function wherein x is greater than 2. When we graph a piecewise function, we always start with the restriction of, in this case, x less than or equal to 2. I'm going to have a point at 2, comma 3. I plugged in 2 into this right here to get 2 plus 1, of course, to be 3. Because I want values less than or equal to 2, I picked 1. If you plug in 1, you get 2. Turns out because this is a less than or equal to inequality, it's a closed point at 2, comma 3. And then the other point after that, every point after that for that matter, is always going to be closed. So there's your partial line. It's a piece. Now if I had drawn the full-fledged line, I would have actually erased, and you can try this as well, I would have erased everything to the right of 2. So that's another way to kind of go through it. As the directions say, erase the part that you don't want. For the second piece, I went ahead and I made a point at 2 comma something, 2 being an open circle because it's a greater than, not a greater than or equal to. So 2, you plug it in. 1 minus 2, of course, is negative 1. Every value beyond that, in other words, 3, 4, and so on, greater than 2 is what we were choosing. I picked 3. 1 minus 3, of course, is negative 2. So we've got an open circle at 2, negative 1. I've got a closed circle at 3, negative 2. There's the second piece. And notice, again, I don't have the left side of the graph. In other words, if it were a full line, you would then erase that piece because you only want the graph of x greater than 2. Open circle, and then graph down and to the right. The last part of our lesson today is even and odd functions. Even functions are symmetric with respect to the y-axis, and odd functions are symmetric with respect to the x-axis. Note the following test. In order to determine whether or not a function is even, f of negative x is going to be equal to positive f of x. Odd, f of negative x will equal negative f of x. As a tip, whether you are testing for odd or even, you start out the same way. In other words, with f of negative x. Now I'm going to go ahead and show you guys one example. You will finish with the other two on your own. So here's the function. You're going to plug in a negative x everywhere you see an x. So in this case, negative x to the fourth minus the absolute value of negative x. This quantity is positive when you simplify it. You leave it as a variable. An absolute value of a negative is always a positive, and I actually left the absolute value there because technically it's always going to be that way, always going to be positive in this particular regard. Because this result is the original function as it turned out that we anticipated, whether it was even or odd, In this case, because it ended up being f of x, we decided, oh, there you go. It is in fact even. It's not odd. Please look at the last two examples on your